Hey guys, this is Kelly Cox, and I'm going to show you two proofs of the 3n plus 1, 3x plus 1 Collatz conjecture. The first thing I'd like to start with is the understandings. And it basically comes down to this. When you divide a number, you're removing a 0 from the end of it, a power of 2. So n divided by 2, you will always find an odd number. The last one you'll find is the number 1. When you do 3n plus 1 divided by 2, you're going to end up at some point with an even number even after dividing by 2. So 3n plus 1 divided by 2 will always find an even number. And so this proof is just to show that every number will find the 4 to 1 loop. It's not to show every number will eventually get below itself. To me, that should just be an understanding when looking at this. So what I want to do is first show you I started building an Excel file to play around with this and look at things, and this is what I ended up with. The first column is all the even numbers. Column H has all the odd numbers, and I have the number 1 in H2 column. That number builds all the other numbers that you see that are changeable. So if I change that number 1, everything else will change because it's based off of a 1 being in that spot. So it shows that I can build to any number I want, an infinite number, and I can still get back to the number 1. So the plus 1 column has all these blue numbers, and they correspond to even numbers that doing the 3n plus 1 gives you. So the first one would be 3 times 1 plus 1 gives you 4, so you end up at 4. So they're color-coded that way. If you go ahead and do the divide by 2, half the time you'll get an even, half the time you'll get an odd. So those are shown in the light green of the even and odd. Those are the numbers you can get to. The numbers that are uncolored you cannot get to from an odd number. And you cannot get to the maroon ones from any odd number because they are mod 3. The next column is column K. It has my formula that I rewrote so that I could find positions with the n minus 1 divided by 2. And so it gives the same result. So if I click on any of these, you'll see I'm using my formula to get the results, even though if you divide 76 by 2, you'll get 38. The next one is positions. It tells where you're going to land on the position chart. It'll match so 74 is position 37. If I go over here to 74, you'll see that 37 is there. The next thing is cycles. What I discovered is that every other odd number has a cycle tied to it, and they increment by 1 to infinity. And then I can see for these cycles to give me more information. But I use the position Pmod 4 to find the information for all my odd numbers to start with. And then to clean it up a little bit, here's what I ended up with. So I have all my positions in gray, all my even and odd numbers are in a dark gray. And what you'll notice that if I mod the number itself, even numbers can, at mod 4 can only be a 2 or a 0, and the odd numbers will be a 3 or a 1. But if I move to positions 1, 2, 3, 4 to infinity, I can mod the position and I get 1, 2, 3, 0, 1, 2, 3, 0 cycles. So by taking the even and odd numbers and matching them to a position, I can now mod for the position and know what the odd number is going to do. The even numbers are all just going to divide by 2. So we always know what an even number is going to do. But what the odd numbers are going to do is going to be determined by what position it is, a 0, 1, 2, 3, which one of those it is. And if it is a specific position, then I need to look at the cycle mod 4 to tell, there's 5 patterns that emerge from what the odd numbers can do. So one of the positions has 2 different results. It can be even or odd. It's based on the binary. And so you have to look at the cycle mod 4 to know which one of those 2 it's going to follow. And so I've written let me drop this down. I've written in RStudio a script that I can plug in any number and it'll give me the start and steps for that number. And one of them that I want to look at is this number here, 107, I guess it's 1 billion. But you can see using my formulas, I can compress this down to 12 steps to get from that number to the number 1. And what that looks like over here, if I go to this website that is a 3x plus 1 calculator, I can put in that number and it actually is 82 steps. So I can skip a lot of steps by looking at the mod of that number. And what's cool about this number is there's 10 ones to begin with, and then 0, 1, 0, 1, 0, 1. So when you look at a number like this, it's mod 2. That means it ends with a 1 and a 0. So that what happens next with my script is it looks for the first pair that match. So it looks to here and it skips the first 20 binary numbers and sees these two and says, well, I can go to the 21st power of 2 and divide by that, and it immediately gets, it skips all those down to this 1535 that you see. So it knows it's just going to remove a bunch of zeros till it gets to this number. And what that looks like, let me show you real quick. In Excel, you put this number in, and then it just does a mod 2, mod 4, mod 8 until it finds this number here that is not mod 21 0. So it knows that it needs to divide. So it takes this number and divides the billion or the 3 billion number by a million, and it gets the 1535. So another cool thing you can do is put in, I'm going to put in a number 2 to the power of 100 divided by, or minus 1, and I get this number here, which is, right, to the power of 100, so I have 100 ones, and when I add 1 to it, I get the 101st 1 with a bunch of zeros behind it. But when you subtract 1, you get 100 ones in binary. And what this tells me is I'm going to go up 100 times before I find that first pair of even numbers. And so going up 100 times means we're going to be dividing by 2 99 times. So I have to go to step 200 to find my 2 evens, right? I hit an even number at 199 and then I get a second even at 200. So I can know from the binary how high this number is going to climb. So I'm playing with a number that's well beyond the known where they've checked all the 3x plus 1 numbers. I think they're up to 2 to the power of 62, 64 range. So I'm playing with a number that's 40 above that. And with my computer's calculator, I can go to 2 to the power of 104, and I don't have any issues with any number that I put in below that. But you're always going to see these numbers doing these same things. You can look at the ones at the end and know how high it's going to climb. And so the number 27, plug it into my script, and it only takes 27 steps to get from 27 to 1. And the highest number you see is 3077 instead of the 9000 that it climbs to doing it single steps. but I'm able to skip those because of the mod that they are at. And then another number that I did is this 9 million, 95 million. But let me show you this. The 1 billion, you can see all these numbers that are gray are even. So you're going to divide by 2, but since they're even, I can go from this position mod 2 to the next odd number, which is the 1535. And then I can skip from here, 1535, I can skip to the next green one by taking 1535 and adding the collapse numbers over here. I add all these collapse numbers to the 1535 and it will give me 39,365. And then from a mod 2, I can skip all these gray numbers because they're even. And I'll get to the 7038. And so if we scroll back up, you'll see 1738. The next thing is 137, which is the next green, 65, 37. So all these are skipped, and then it's going to skip from 37 to 7, and from 7 to 17, so it can skip odd numbers that are mod 3, mod 1, and go straight to the next ones that are green. And so nope. There we go. So I put in this 95 million number. You can see it takes 33 steps by skipping all the even and duplicate or the collapsible odd numbers. But in reality, it takes 125 steps to get to the number 1. And this is, again, I can skip all even numbers. So skipping, a huge skip from 108 million down to 10 million, down to 3 million, down to 1 million. And so forth. All right, 191,000 down to 2,000. Because you have these numbers with a lot of zeros at the end of the binary. And so, right, we're just going to divide by 2 till we get rid of those. With the odd numbers, right, an odd number means that the last digit in the binary is a 1. And we're going to remove it till we get to a 0, and then we're going to divide by 2. But you're just, with 3x plus 1, you're just removing ones from the end. So let me give you some definitions that I use. The first one being prime locations. And what I mean by that is the numbers are multiples of 6x plus or minus 1. And so the first set is 5 and 7. These are the first two prime locations. And they are the first two, both of these are primes. The previous primes, 2 and 3, build the 6 block. And so nothing that's a 6 can be a prime. So every number that is prime after 2 and 3 is a 6x plus or minus 1, 5 being the first one. And 5 times 5 is 25. 25 is a prime location, but is not a prime because it's a multiple of 5. But it is a 6 times 4, 6x plus 1, 25. So it is a prime location. N in my formulas is going to be numbers, the number that we're dealing with. P is going to be the position. NP will be new positions. C is cycles. R is my formula, which gives you the same results as 3n plus 1 divided by 2. It's just broken out differently. And then steps. 3n plus 1 is going to equal 1 step. 3n plus 1 divided by 2 is 2 steps. My formula, the R formula, is 2 steps. And then the most recent one that I've discovered that I use, that can be used to find the Collatz numbers, is the one that I just presented you, n plus 1 divided by 2. And then we're going to talk about mods. So you can, the mods that I deal with are in the number itself. So n mod 2, 3, and 4. P mod, which is the mod of the position, which P mod 4 is going to be my primary mod that I look at. And then cycle mods, we're going to look at C mod 4 as well. So just go through the basics real quick. Starting information. We're talking about any number that's positive and a whole number. If it's an odd number, we're going to multiply by 3 and add 1. If it's even, we're going to divide by 2. And since all odd numbers give an even result, we can do 2 steps at once with the 3n plus 1 divided by 2. And then I have my own formula that I use for this calculation. And if you want to go from the even back to the odd, the formula is n minus 1 divided by 3. I have all my numbers set up in positions, starting with position 0, which is 0 and 1. 1 would be 2 and 3, 2, 4 and 5, 3, 6 and 7, and so forth to infinity. To find a number from the position, you do position times 2 plus 1 for the odd, and position times 2 for even. To do the opposite, you're going to do n minus 1 divided by 2 for odd, and n divided by 2 for even numbers. What does knowing the mod of a position tell us? On the even numbers, you can mod 2 and mod 4 the number. If it's both mod 2 and mod 4 0, then we know the next number will be even. If mod 4 is a 2, then we know the next number will be an odd. 50% of even numbers will be even, the others will be odd. If it's mod 3, then it will divide down till it hits an odd number, and then it will leave the mod 3 and not return. You're cutting the number in half every time. With odd numbers, after you do a 3n plus 1 divided by 2, your max add is 67%. This is far less than all our even cuts. So as you're playing with numbers, looking at them, you're drastically getting closer to 1 as opposed to moving away from it, even though doing the 3x plus 1 feels like you're getting farther away. You're actually not moving away as fast as you're falling towards it. The actual amount is the number that is n plus 1 divided by 2. So it sits at 67%. When you're playing with the smaller numbers, it gets a little bit less than 66%. From odd numbers, I can only start with a mod 3 number, and then I immediately exit 3, 6, 9, 12, 15. You can't hit these numbers unless you start with them. So now let's talk about the actual formulas that I use for each position. So I'm going to p-mod the number by doing the n minus 1 divided by 2, and it's going to give me a number. I'm going to p-mod that number with a 4, and if it's a 0, I know I'm in a 4 to 1 loop and that my next odd number is going to be 3 steps away, and I can tell, right, that my new position will be position minus p divided by 4. So the first p mod 4 0 is the number 4, and so it's actually the number 9, so it's position 4, so it's mod 0. And so when you take the position 4 and you divide 4 by 4, you get 1, and it's going to be, so position minus 1, so 4 minus 1 is 3. And so if we look at this, 4 minus 1 is 3, 7. And so if you do the math for the 3x plus 1 for 9, it goes to 28 divided by 2 is 14, and 14 divided by 2 is 7. So in 3 steps, I'm 1 position less than where I started, and it just goes to infinity. So the farther you get away from the number 1, the more drastic you're going to drop in those 3 steps. All right, so if I go up to a position scientific, so position 1000 times 2 plus 1. So we're looking at the number 2001. So 1000 mod 4 is 0. So it fits our P mod 4. So 1000 divided by 4 equals 250. So we're going to drop 250 positions. So 1000 minus 250 equals 750 times 2 plus 1 means that when you have the number 2001, after 3 steps, it's going to be 1150. And so let's take a look at that. So if I put in, awesome, 2001, I hit enter, I get nothing. Gotta love it when okay, so if I put in 2001, it goes to 6004, 3002, and then 1501. And it went from position 1000 to position 750. So I can know with certainty every fourth number is going to drop after 3 steps. And so I can skip the two the two even steps between those and just go straight to this, where I can do this calculation and know where I'm at. And so just to find the numbers that you need to, you would do P equals n minus 1 divided by 2, and the number would be new position times 2 plus 1. So P mod 4, 2 is the only one that is even after 3 steps. So now with that new formula that I figured out, I can skip even beyond 3 steps here. I can find the next odd number by looking at the powers of 2, modding, I take the number and P mod 2, P mod 4, or n mod 2, n mod 4, n mod 8, n mod 16, till I find the mod that does not give me a 0 result. And then I know that's how many even numbers I'm going to go through to get to the next odd. And so I just divide by that number that it gives me. And so you have to know this formula here, and it has some duplicates that are adding and subtracting from each other, so you can simplify it into this number. But you take the number, you add 2, subtract 1, divide by 2, add 1, divide by 4. And so it will give you the new position, and here you just multiply by 2. It's going to be an even number after 3 steps. And this will give you the position and the number of it. Pmod 4-3, after 2 steps, you're going to be at your next odd number. So here, Pmod 4-3 means we're ending with at least, in binary, at least 2 ones. I could have an infinite amount of ones at the end of the number, and I'm just going to cycle through those till I get down to the Pmod 4-0. But when you get to 2 ones at the end, you're going to be Pmod 4-1. And so you go Pmod 4-3, and then it will sit there till you get down to 2 ones at the end of the number. Then it'll switch to Pmod 4-1, and then the next, in 2 more steps, it'll be Pmod 4-0 or Pmod 4-2. But after 2 steps, your new position will be the position plus the cycle. And here's the formulas to calculate the numbers for Pmod 4-3. And then, like I said, the last one, Pmod 4-1, has 2 different ways to look at it. Again, with this one, I can look at, after 2 steps, this is where I'll be, Pmod 4-0, and look at those calculations. But I can also, right, if I look at the CMod and it's CMod 4-0, I know that in 5 steps I'll be here. And I didn't think I could do this if it was CMod 4-1, but I've since figured it out. So I can do 5 either way, but in actuality, I do, with my formula, I just go 2 steps and get the Pmod 4-0 and then skip all the even numbers. But after 5 steps, if it's CMod 4-3, it will be an odd number in 5 steps. So I can jump to that 5th step. If it's Pmod 4-2, it's going to be an even number after 5 steps, and I don't want to touch even numbers, so I was just going to the Pmod 4-0 or 2, whichever one it hit here, and I would just skip, I would recalculate from there and not try and jump 5 steps. But there's all the to find the numbers you need for these calculations. So now let's look at the binary. And this is where I don't hear a lot of talk. I think a lot of people tried to figure out something binary, and they're looking at it from a perspective of multiplication, and it's actually needed to look at it with addition. So you have the 3 formulas: 2 times n, 3 times n, and 3 times n plus 1. And when you look at these from an additional perspective, with 2 times n, I'm basically going to, from a binary perspective, add what I have to itself. So if I have 1, I'm going to add 1 to it, and I'm going to get the results. So 1 plus 1 is 2. 1 times 2 is 2 as well. So if I do 2 plus 2, I get 4. 2 times 2 is 4. And so on. But you're just taking the binary code and adding it to itself. With 3n, you're doing the same thing, except you're throwing a 0 at the end of the number. So if I have 1, I'm going to add 1 0 to it. This is the same thing as multiplying by 3. And so when I do that, I get a binary number of 1 1. So if I take 3 1 1 and I add 1 1 0 to it, which is 6, I get 9. And if I multiply 3 times 3, I get 9. So when you're looking at this conjecture, right, we're hearing multiply 3 times n, but from a binary perspective, we're doing the same addition as we are with 2n, but we're adding a 0 to the n. And now when we do 3n plus 1, all we're doing is taking that 0 and flipping it to a 1. And so I'll do 1 plus 1 1, and that will give me the 4. All right, and if I do 3 plus 6, but it would be 7, I'm going to get 10, 1 0 1 0. And so when we start talking about binary, I only care what's in the last 3 spaces of the binary number. It does not matter to me what's happening from the power of 8 and beyond, because I know that what's going to happen is going to happen based on the last 3 spaces of that number. And so 1 1 1 is 7, 0 1 1 is 3, 0 0 1 is 1, and 1 0 1 is 5. And then it's showing S mod, it should be C mod. And then it shows you're going to go from S mod or C mod 4. You can look at them and know where you're going to go next. And then from the even, 0 0 0 0, 0 1 0 is 2, 1 0 0 is 4, and 1 1 0 is 6. So looking at the last 3 spaces, right, we can p-mod it and know what's going to happen. And so just to give you a little visual, if I take the number 15 and I multiply by 3, I get 1 1 0 1, and if I add 1 to it, it takes the last 2 bits and adds 1 to it. So in this case, it's just shifting the 1 over 1 spot. The red and blue are never going to change. So if I increment from this point, if I add a 1 in front of these, I get 31. And you can see that green is staying the same. If I add another 1, it shifts the 1 out 1, and nothing's happening to the red blue and yellow numbers. It's just everything is happening to the left, and I don't care about it. So now I've added another one. I've got 2 ones, and you can see that they're just staying there till they fall into this last piece. You know, there'll be changes, but it's not going to matter. And I add another one, I get 100. I add another one, I get 101, 110, 111, and then you can see it's 111, and it doesn't change. So the ones that are tied to the red are going to get eliminated along the way. They will not change. If they're tied to the one at the far right, they're going to be removed with it. You know, you can just count. This 127 has 7 ones. You're going to, for the next 2-step cycles, you're going to remove those 7 ones one at a time. And so what does that look like? So if we take this number, 10 billion, it ends in 8 ones. And then I'm marking that 0. That 0 will continue to stay there. What happens to the left of it, I don't care. Because I know what I'm going to do is remove 8 ones. And so if I look at this, you multiply by 3, add 1, and you see it created a 0 in that last spot, and it threw the 1 above the yellow marker. And so then we're going to divide by 2 to get rid of the 0, and so now we have 7 ones, and the yellow fell to the right with it. And what's happening to the left of the yellow, don't care. And so we multiply by 3, add 1, and we get another 0 at the end, and it threw a 1 into there. When you add 1 to 1, what do we get? We get 4. And so it shifted this last one over 2 spots. And so then we divide by 2, and we're left with 6 ones, and all the other numbers fell 1 slot. We multiply by 3, add 1 again, we kick another 1 out there, and it's gone from the right side. And so forth down to, now we're down to 3, 2, 1, 1 left. Now again, like I said, my formula, when it sees 1, 0, it's going to search out for the first pair of 1s. And so it knows the next number is going to be end in 0, 0, 0, 0, 0, 1. And so if I look at this, right, I multiply by 3 and add 1, it removes all those 1s in there and turns them into 0s, and we're left with the 1 here. And all these 1s tied to this one are now linked to it. So we're going to divide by 0 5 times, and then we're going to remove these 6 ones. So it's just going to come down, and here you see 100, which is 4, 2, 1. Right, so we just did our first 4, 2, 1 loop with this number. And it's got 6 ones it's going to remove. Now, if we continue looking down the line of this number, we come across this 159, 617, which is 100. So it immediately matched 2 zeros, which means we're going to do a 4, 2, 1 loop. So there's 4, 2, 1. And it hit another double 0, so it's going to do another 4, 2, 1 loop, another 4, 2, 1 loop, and this time there's 2 1s. So when it gets to here, now it's got to eliminate more than 1 1, so it's going to remove 1, and then we're back to a 4, 2, 1 loop. Now we're going to do one more, it's 1 0 and then a pair of 1s, so we're going to do an 8 4 2 1 loop. So to look at another number, this is mod 3 because there's more than 2 1s at the end. So this one has 12 1s, and it's the first one, I believe, that has 12, 40, 95. And it's going to do the same thing. It's going to stay mod 3 till it gets down to the last one that it's eliminating. So now we have the one left. You can see it's flipped with 2 1s at the end. It flipped to a mod 1, and it's mod 1. So now it's going to go to either a mod 2 or mod 0, and it went to mod 2. And so you see here it's 1 0 1 0 1 1. So it's going to do a 1 with 5 zeros at the end. So 32, 16, and so forth. So here's this 2 million, right? 2.5 or 2.5 billion number that ends with 12 1. So it's mod 3. It's going to do the same. If you look, the only numbers that are different are going to be above the yellow. And we don't care about those because we know that we're just removing ones. And so we get down here, it's 1 1. It flips to 2. And this one says 1 0 and then a pair of 1s. So we're going to go into a 8 4 2 1 loop. And so if we look at the number 27, it's 1 1 0 1 1. So we're going to go up twice. So we're mod 1 starting off. And so it goes, so it has the 4 2 1 loop at the end. So it's mod 0. So 4 2 1. And now we have 5 because we're at number 31. It's the first number that's all 1s with 5. And so we're going to mod 3 down to 2. And you can see here, we're going to go to mod 0 because we're in a 4 2 1 loop. Another mod 0, 4 2 1 loop. And this is mod, it flipped to mod 3. So I know I'm going to have multiple 1s, but there's only 2. So when it hit when it divided by 0 the last time, it went to mod 1, mod 1. And we're going to go to mod 0 again, 4 2 1 loop. And now we have 3 1s. So we're mod 3, mod 3, mod 1, because now we're down to 2, mod 1, and we're going to go to mod 0, 4 2 1 loop. And now we have 175, which is 4 1s below the yellow. So mod 3, mod 3, mod 3, mod 1, mod 1, and at 001 is coming down, so we're going to mod 0, 4 2 1 loop, and you see it didn't do mod 0, so we're going to search for the first pair, and it's a 8 4 2 1 loop. It's mod 3, mod 0, so 4 2 1 loop, 425 is 4 2 1 loop, and we hit 319. 319 is where this number confuses people, because it hits this number with 6 1s in it, which means it's going to climb 6 times now. There's nothing unusual about this. We have lots of numbers that have 6 1s in them in binary at the end. And so it's going to climb. You can see it, all these yellow numbers, or the gray ones in between, are going up. Here's our last number. So it climbed from 319 up to 2,400. But now we're going to do a 8421 loop. So 0, 2, 1, 1. And now we, right after immediately getting a 6 count climb, we hit another 911, which is 4 ones at the end. So now we're going to go up 4 more times. 2, 3, and we hit this 9,232. But if you look before it, 10100. So now we're going to do a 168421 loop. And we hit 100, so we're going to do a 421 loop. 421 loop. So now we're, we went up to 9,000, and in just a matter of a few steps, we're almost back to 319, right? 325 right there. And we hit it on a 1 at the end, 10100. So now we're going to do this 16 cut. So we hit this 976 because we multiply by 3, but now we're going to divide by 0 4 times. Right, so now we're at 61. We're still not below 27 where we started, but we're getting close. And you see this 1011, so we're going to do a 8421 loop. And we have 3 ones. We're now below 27, so we know it's going to go to 421, but it goes from 23 to 70, and then does its last climb and ends with a couple of high 0 numbers. 160 and 16 goes 8, 4, 2, 1. So as you can see, there is no number that's not a binary of 1 and 0s. So and again, I'm not looking at anything beyond the last 3 pieces of the binary. I mean, there are some cases where I can look and know how many how far I can skip ahead, because if I have 100 ones at the end, I know I can skip to step 200 by just collapsing all those. And so I have a formula to do that. So if you have any questions, drop me a comment, and thank you for watching this video.